For this lesson, we're going to be talking about how to take the area between curves and rotate that around an axis. So for example, we have the area between f of x and g of x. So I'm only taking, and we'll say this is A, and we'll call this B. So we're taking this area, and we are rotating that around the x-axis. So creating my symmetry will look something like this. And let's see. This. And remember, you can pause the video if this is going too fast. So we're rotating that area around the x-axis. And we do need to work on visualizing what this looks like. So I'm going to do my outer disk first. So it's going to look something like that. Oops, it's far too over. It's going to look like that, kind of. But I'm also going to have inner disks. And you do have to use your imagination on what this looks like. But it's going to look something like this on the outside, right? But on the inside, you kind of have this like bell shape cut out of it. So it's going to be solid, but then the inside will be cut out. So it's like if you had, for this particular solid, it's like you have a bowl on the outside. So if you were like to look at it from a few feet away, it looks like a bowl. And then when you get closer, you notice that it has this kind of like weird vase shape cut out of it. So we have empty space. So this is unlike the disk method. The disk method is just everything is completely solid. You take a slice and it's a completely solid slice. In this case, if you took a slice, so let's say I take a slice in the middle. If I were to take a knife and I were to take a slice of this, cut it open, I would have something, so I'll kind of draw a picture of what a slice would look like. I would have still a circular figure, but it would have a hole in it. So it'd be like solid, but with a hole cut out of it, because you have this like inner bell shape, this inner vase shape that is not filled in. That part is empty. So a slice is what we call a washer, which is why this is called a washer method, as opposed to the previous lesson, which was the disk method, where a slice was a completely solid disk. So a washer is really a big disk minus a smaller disk. Okay, it's taking a disk and then you cut out another disk. So if you think about the volume of a washer and knowing that it is a disk minus another disk, what I'm going to do here is just, create different radiuses. So looking at my original figure, when I'm rotating around the x-axis, my larger radius is going to be this distance. It's going to be the distance to the outer function. Distance to outer function. But the piece that's being cut out, that radius, goes to the inner function. So the radiuses are different because, again, you're going to have a larger radius and a smaller radius cut out of it. But what about the heights? Are the heights of these cylinders the same? Is the thickness, so remember H represents the thickness. is the thickness of the disc, or the washer in this case. And the thickness is the same, because again, we're taking a slice. So it's not that like if you take a slice of a donut, like take just the very insides. So I slice off the left side, slice off the right side, I'm left with this like washer looking thing. Well, the thickness of that slice is going to be the same no matter if you're talking about the outer part of the donut or the hole that you've cut out of it. The thickness is still going to be the same. So that's why I've left them both H, because they are the same thickness no matter where you're at, inner radius or outer radius. And the thickness, of course, is going to be dx, because you are adding up an infinite number of these discs that are all next to each other. They're all different radiuses. I'm just making my picture messier, I'm sorry. But I have all of these washers that are sliced, and they are all directly next to each other. They're stacked next to one another. And the thickness of that slice, because I have an infinite number of these washers, will be approaching 0. So an infinite number of slices that are infinitely thin. And the way I represent that infinite thinness is dx. So I can factor out a pi and then I still have my radiuses squared. I cannot factor out a squared, like it has to be r squared minus r squared. But I can also factor out the thickness because that will be the same for each of these outer disk and inner disk. So the volume of the solid will be pi, and I'm going to go ahead and just keep the pi on the outside, because remember that you can factor out constants. So pi, and then I'm going from a to b, whatever my bounds are, and then it's going to be r squared, big R squared, minus little r squared, and the thickness is dx. And then the question is, well, what's big R squared and what's little r squared? So remember that big R goes to the outer function. In this case, that's f of x. And then my inner function was g of x. So that's the outer function. It's the one that's furthest away. It's going to be the longer radius, or gives us the longer radiuses, radii. And then g of x is going to be the inner function. So that part's important, that you always have outer function minus inner function. Outer function squared minus inner function squared, I should say. Okay. So that is the volume of a solid using the washer method rotated around the x-axis. But then what if we rotate around the y-axis? So again, I'm going to create my symmetrical figure here. Looks like this maybe. Yeah, that's close enough. So the outside is going to look like, oh, actually I need A and B values first. Let's say my B is here and my A is here. So I'm taking the area between f of y and g of y, taking that area, and I'm rotating it around. And when I rotate around the y-axis, now my washers are going to be vertically stacked instead of right next to each other. So that's terrible. Let's try that again. Something like that. So the outside would kind of look like this. That's what the outside would look like. But the inside kind of has this like funnel cut out of it. So the inside is going to look something like that. All right, so the volume of one of my washers, washer, is going to be pi times the larger radius squared times the thickness minus pi times the inner radius squared times the thickness, which again becomes pi big R squared minus little r squared. And the thickness in this case, if you're looking at your representative disk being rotated around, the thickness of that disk is now dy, because you are stacking them on top of each other. It's going to be the distance of your y values. So go ahead and let that be dy, which means when I find the volume of my solid, and I'm doing from A to B, big R squared minus little r squared, the thickness is going to be dy, which means my A and B values need to be in terms of y. They're the y coordinates. And then my function will also need to be in terms of y. So my outer function, the function that it touches on the outside, would be f of y in this case, not f of x. And then my inner function is g of y. It's the one that's closest to my axis of rotation. All right, so we're going to find the volume of the solid of the area between x squared plus 1. So I'm going to go ahead and graph that. And x plus 3. And since it's the area between that, this is the area I'm talking about. Oops. It's supposed to be here. There we go. So that is what this side will look like. Fill it in to try to create a three-dimensional figure here. Oh, this one turned out pretty lovely, actually. So you can see that the outside, I would see kind of this cone figure-ish. The outside would be a cone, but on the inside would be like a vase cut out of it, or a funnel-looking thing. But on the outside, if we were just to look at it from afar, all we would see is the big cone. So let's go ahead and start setting up my integral. So it's going to be pi times big R squared minus little r squared. The thickness is dx because we are rotating around the x-axis. So the thickness of my representative washer here, the thickness would be dx. That's the thickness. So that means that my functions need to be in terms of x and my bounds need to be in terms of x. So looking at where this area intersects, it intersects first at x equals -1, and then again at x equals 2. So those are my bounds, because I started with the area between these two curves. And then my outer function is the line, x plus 3. And then the inner function is the one that's closer to the x-axis, which is x squared plus 1. So remember, this is the outer function, and this is the inner function, and they are being squared because it's pi r squared h. And then from here on, you should be able to do this yourself. So if you want to, you can stop the video and just solve it on your own. Otherwise, let's just review how to solve integrals. X to the 4th plus 2x squared plus 1 dx. And then I can combine like terms, which is -x to the 4th. X squared minus 2x squared is -x squared. Plus 6x plus 9 minus 1 is plus 8 dx. Find the antiderivative, -1/5 x to the 5th minus 1/3 x cubed plus 3x squared plus 8x. -1 to 2. So if I plug in 2, that's negative 32 fifths minus 8 thirds plus 4 times 3 is 12 plus 8 times 2 is 16 minus, plug in negative 1, you get positive 1/5, positive 1/3, positive 3, negative 8. Combine like terms here. Negative 32 fifths minus 1/5 is negative 33 fifths. Minus 8 thirds minus 1/3 is minus 9 thirds. Oh, that's nice. Plus 12 plus 16 is 28. 28 minus 3 is 25. 25 plus 8 is 33. If I did that right, because I'm doubting myself. Never mind. I'm pretty sure my arithmetic is right, but if it's wrong, fix it on your end. And I can just leave my answer. Oh, actually, I can simplify a little bit more. Negative 33 over 5 minus 3 plus 33 is plus 30. And I'm just going to leave my answer like this because I don't have any rules that tell me I have to simplify into one fraction. But you guys should know how to do that. It'd be 30 times 5 is 150. 150 minus 33 is what? 122? No, 112? Be 112 over 5. Oh, and it's technically units cubed because it is the volume of a solid.